vesicle membrane with presynaptic membrane. And in the box release of neurotransmitter, what is the process? What is the name?
Excreted. With ATP.
Actually, ATP energy doesn't require for exocytosis, endocytosis. But exocytosis doesn't require. But this process is unclear exactly in modern science. I don't think about it.
Okay.
You must know preterm docked vesicles, fusion, and
Exocytosis.
term exocytosis. Well, exocytosis, third process, that's one process, second process, also calcium channel, and third process, exocytosis. Exocytosis. Second function of calcium inside bulb, stimulation of movement, new vesicles to presynaptic membrane and docking, like cycle. One vesicle released, next must be prepared, cycle. After exocytosis, empty vesicle, empty vesicle, form new vesicle, empty vesicle, and go to inside and filled by new neurotransmitter. You see, cycle. Released, new empty vesicle, filled with energy, ATP pump, new neurotransmitter, and work again. Next part, postsynaptic. Fourth process, diffusion of neurotransmitter, diffusion to postsynaptic membrane, and binds to what?
Receptor. Ligand receptor.
Receptor. Binds to receptor. Inotropic receptor, this neurotransmitter. Inotropic receptors is located directly on channel wall, on the channel wall. This ligand-gated channel contains inotropic receptor cells. Inotropic receptors. This inotropic receptors is a part of ligand-gated channel. It's a one structure, single, common structure. When neurotransmitter binds to receptors, for example, acetylcholine, binds to nicotinic cholinergic receptors, it immediately opens ligand-gated channel. And ligand-gated channel passes ions. We have two types of synapses with different effects: excitatory and inhibitory. I will explain mostly now about excitatory. In excitatory synapse, with inotropic receptor, most commonly this channel permeable for several ions, at least sodium and potassium equally. Channel regardless, for channels regardless, sodium pass or potassium is whole. So sodium can go inside in accordance with concentration gradient, or potassium can go outside. In accordance concentration gradient, ligand-gated channel can pass both ions in both directions, sodium inside, potassium outside. But it doesn't, it's useless. It's useless. It's necessary to transmit signal. But we know that driving force, who answer driving force? I don't know the name. Driving force for iron fluid. I'm talking yesterday. What is a driving driving force? Concentration gradient. And second? We discuss about ion flow across channel. Yesterday we had long discussion about it. I want you repeat.
Permeability and
What is the driving force to provide diffusion of ions across channel?
can I translate؟ میگه چیزی که دیروز بهت گفتم و بگو، همونی که سوال تو آقای معظمی و اینا بود.
Concentration gradient and second gradient. There's two gradients exist. Concentration and what gradient more? Obviously. Produce, remind, recall. What gradient exists more? Electrical gradient. Electrical gradient. Electrical gradient is the distance between just membrane potential and equilibrium potential for ions. Remember, recall from previous class, what is the equilibrium potential for potassium? How many millivolts? Minus?
7,
No, 70, more.
90.
95 minutes. What is the equilibrium potential for sodium? Plus
30.
Plus 50.
50.
55 maybe. About 55. Plus 55. What is the resting membrane potential in Europe? RMP.
Minus 70.
Minus 70. So electrical gradient for potassium low, no? Electrical gradient, no? Difference between minus 70 and plus
55.
That big. No? So electrical gradient for sodium is biggest. And in this case, sodium will be go inside mostly. And potassium a little. Yes, we don't pay attention for potassium. No? Mostly sodium. Well, next part. Sodium goes inside and depolarize membrane. At first, sodium provokes local potential. Sodium influx provokes local potential. Local potential, what is the name? Local potential in Europe. What is the name? Local potential in synapse. Yes. No. Name. Name of local potential on the postsynaptic membrane. P is P. What does it mean?
Excitatory postsynaptic potential.
Yes, excitatory postsynaptic potential. Copy picture because it will be my question during colloquium.
It's about this.
Exactly some card. Now, EPSP is simple graph. But to understand the principle, it's local potential. If EPSP reaches threshold, it converts to action potential. But in neurons, EPSP amplitude very, very low, about 1 millivolt in neuron. Only 1 millivolt. Threshold minus 50. Is it enough to have only a single EPSP to reach threshold? No, of course. It's necessary to have summation. So in neurons it's impossible. What happens in muscles? Muscle excitatory synapse has some properties. At first, it's called neuromuscular joint. Neuromuscular joint. And what is the second name? End plate. Motor, end plate, or end plate. Motor,
Huge.
with big space, big distance. And it has sides with concentration of a lot of vesicles and a lot of receptors. You have pictures in my presentation. A lot of vesicles, a lot of receptors under vesicle docket. What is a neurotransmitter? Motor plate. Acetylcholine. Acetylcholine. What is the receptors type? Nicotinic. Nicotinic cholinergic receptors. I will write shortly. Nicotinic. Remember that nicotinic cholinergic receptors, the scheme is inotropic. Inotropic, it's very important. Inotropic receptors provides faster synaptic transmission. Inotropic, simple transmission, inotropic receptors. End plate contains a lot of vesicles releasing neurotransmitter during synaptic transmission, contains a lot of nicotinic cholinergic receptors, and provide big EPSP. Big EPSP, resting member potential minus 90 in skeletal muscle, big EPSP, it's called end plate potential, amplitude about 30-40 millivolt. It reaches in healthy muscle, it reaches hamisha, always threshold, and above action potential. So muscle responds, normal, healthy muscle with normal synapse responds 100% to stimulation, to each action potential. Muscle is solder. Skeletal muscle must only respond to signal from the brain. Neurons must think. What is the thinking of neurons? Is summation of EPSP, or in inhibitory synapses we have IPSP. What is the difference? Inhibitory synapses. In inhibitory synapses, the process is the same, inhibitory, except ligand-gated channel permeability and postsynaptic membrane. Inhibitory neurotransmitter, for example, again, inotropic receptors, open ligand-gated channel for chloride. What happens with chloride? Influx or outflux? Chloride.
Influx.
Influx, chloride. It provokes hyperpolarization. Not so big because it's near equilibrium potential for potassium, resting membrane potential, but anyway we have hyperpolarization. It's called IPSP. IPSP, easy, inhibitory postsynaptic potential. EPSP, excitatory, IPSP, inhibitory, easy. Inhibitory. Second case, more rarely, but it's possible. Open another type of channel, potassium channel. And potassium go outside, and again we have IPSP, but more frequently chloride. And what is the last step of synaptic transmission? What happens with neurotransmitter? After synaptic.
Must be broken down by the enzymes and the
It should
postsynaptic.
disappear. It must be cleared. Synaptic cleft must be cleared with breakdown In motor plate, it breaks down
With enzymes.
enzyme acetylcholinesterase. It located on the postsynaptic membrane and breaks to acetylcholine, and acetylcholine then uptake. Second most common event option, reuptake. Reuptake with neurotransmitter with protein. It takes a neurotransmitter and come back to synaptic bulb and again used. So neurotransmitter can be used again and again. It's called reuptake. For example, some drugs against depression, antidepressant, blocks this reuptake proteins for serotonin, and concentration of serotonin increased in synaptic cleft for longer time. Mechanism, scientist or medicine doesn't know mechanism, why it works so. This was the beat brain. Something happens. Nobody knows what happens, but it works. For your homework, your self-education, synapses, what you must know more. Types of neurotransmitters. Amines, amino acids, principal types. Neurotransmitter and synaptic modulation and metabotropic receptors. Did you study biochemistry metabotropic receptors? G proteins?
Yes.
But I will explain during lecture, offline lecture. Offline lecture, I will repeat something about synapse, nerve fibers, and details about synaptic modulation, metabotropic receptors. Not copy my video, no? Something will be new. So, okay, do you have question?